So if you are deploying machine learning models on financial time series, there is this fundamental governance question that, well, it probably keeps you up at night.
Oh, absolutely.
You have this continuous data stream, right? Your model is actively generating predictions. But beneath the surface, the actual underlying data generating process might be subtly shifting.
Right. And it is rarely, you know, some sudden catastrophic market crash. Much more often, it is a quiet structural drift.
Exactly. And if you fail to detect it, you are basically feeding new data into a model trained on a reality that fundamentally no longer exists.
Yeah, in the quantitative literature, we formalize this as the market regime clustering problem, or MRCP.
The MRCP, right?
It is the challenge of identifying the precise timestamp when a sequence of asset returns alters its underlying behavioral distribution. I mean, without solving the MRCP, automated model retraining is essentially just guesswork.
You either retrain too frequently and fit to noise.
Or you retrain too late and you just bleed alpha.
Exactly. Now, the standard approaches to this problem, they usually treat time series as like sequential dots on a line. But for this deep dive, we are looking at a 2021 paper by Horvath, Issa, and Muguruza.
Right. Clustering market regimes using the Wasserstein distance.
Yes, and this paper completely flips that paradigm. Their core proposition is to stop analyzing periods of market volatility as sequences of individual vectors and instead treat them as empirical probability distributions.
It is a massive shift. They move the entire unsupervised learning process natively into the space of probability measures.
Which is such an aha moment. But to really grasp the mechanics of this shift, we have to look at how they construct their data pipeline.
Right. So they start with a continuous data stream of log returns.
Yeah.
But instead of feeding those raw sequential returns directly into a model, they lift the data using sliding windows.
Okay, lifting the data.
Yeah, they introduce two hyperparameters. You have H1, which defines the window size, and H2, dictating the stride or the overlap.
So this transforms the linear stream into a sequence of overlapping segments.
Exactly. And then comes the crucial transformation. They don't treat those segments as vectors in Euclidean space.
They convert each window into an empirical cumulative distribution function.
Yes. Every single log return inside that window becomes an observed atomic point.
A Dirac mass.
Dirac mass, exactly. So instead of a vector of prices over time, we are now dealing with a sequence of shapes.
We are looking at the actual empirical distribution of returns over that specific localized time period.
Right, and establishing that topological view, it allows the authors to benchmark against the, frankly, deeply flawed traditional methods that dominate the industry.
Which we should definitely talk about.
Yeah, the first baseline they challenge is the moment k-means approach, or MK-means.
MK-means, right.
The methodology there is to map your distributions into a Euclidean space by extracting their first p-raw statistical moments.
So you calculate the mean, variance, skewness, and kurtosis of each window.
Project those numbers into a vector, and then just run a standard k-means clustering algorithm on those vectors.
I've always found that approach structurally flawed.
Oh, it is.
Trying to cluster complex market behaviors by extracting a handful of statistical moment is like, well, it is like trying to reconstruct a highly complex 3D object by only analyzing its 2D shadow.
That is a great analogy.
You inherently lose the fundamental geometry of the data. When you project a rich empirical distribution into 4 numbers in Euclidean space, the topological information is just gone.
It is basically a mathematically destructive compression. And when you map a distribution to Euclidean space using raw moments, you immediately face severe scaling pathologies.
Because of the different magnitudes, right?
Exactly. By definition, moments that appear earlier in the sequence, like variance, which scales with the square of the data, they operate on entirely different magnitudes than higher-order moments like kurtosis.
Which scales with the 4th power.
Right. So unless you apply meticulously tuned standardization to every single component, the variance will entirely dominate the L2 Euclidean distance loss function.
The k-means algorithm just becomes completely blind to shifts in skewness.
Totally blind.
And even with standardization, Euclidean projections are notoriously vulnerable to outliers. I mean, a single extreme tail event, say a massive intraday flash crash.
Oh, that will warp the Euclidean distance so disproportionately that your MK-means algorithm degrades into just a rudimentary anomaly detector.
Right, it stops clustering market regimes and just starts flagging bad days.
Which is exactly what leads analysts to the second standard baseline, the hidden Markov model, or HMM.
Ah, yes.
Instead of Euclidean projections, the HMM assumes the existence of latent, unobservable Markovian states governing the market.
But the fundamental flaw there is that HMMs require you to define rigid parametric transition densities, right?
Yes. And for computational tractability, those emission probabilities are almost universally assumed to be Gaussian.
And we know financial returns are notoriously non-Gaussian.
Exactly. So we are caught between two failing paradigms. Euclidean projections like MK-means destroy the shape of the distribution, and HMMs force the data into a parametric straitjacket that completely ignores heavy tails.
So we need a way to cluster natively in the space of probability distributions, but without assuming a Gaussian shape.
And that requirement right there is the foundation of the paper's primary innovation.
Okay, let's unpack this.
The authors propose running the k-means algorithm directly on the space of probability measures, specifically the set of all probability measures on the real line possessing a finite pth moment.
Bypassing Euclidean space entirely.
Bypassing it entirely, yes.
I want to push back on the metric selection here for a second, though, because if we are going to cluster in the space of distributions, we need a mathematical function to measure the distance between them.
A metric, right.
And in unsupervised learning, there are highly established ways to calculate divergence. Why completely avoid something like the Kullback-Leibler divergence?
Well, KL is...
Or, I mean, if we are comparing empirical CDFs, why not use the Kolmogorov-Smirnov statistic? Introducing optimal transport just feels computationally heavy if simpler metrics exist.
That is a fair question. But the mathematical defense for avoiding those standard metrics is actually quite airtight. Let's look at the Kolmogorov-Smirnov statistic first.
Okay.
Ks simply measures the maximum absolute vertical distance between two cumulative distribution functions.
Right. It is just the L-infinity norm.
Exactly.
Oh.
Because it only isolates the single point of maximum deviation, it lacks the geometric sensitivity required to distinguish between complex elements of a clustering set.
Oh, I see. Two vastly different market distributions could theoretically share the same maximum deviation point while having completely different tail behaviors.
Exactly. And the Ks statistic would treat them identically.
It's essentially too blunt. It looks at the worst-case divergence rather than the total geometric discrepancy.
Precisely.
But what about Kullback-Leibler divergence? I mean, that is the cornerstone of information theory. Why does KL fail here?
KL divergence fails because of the specific nature of our lifted data. KL requires absolute continuity. It requires continuous density estimation.
But our sliding windows are empirical distributions composed of discrete Dirac masses.
Exactly. If you attempt to calculate KL divergence between discrete empirical measures that don't perfectly overlap, the calculation mathematically blows up. The divergence just becomes infinite.
Wow. Okay, so to fix that, you'd have to apply aggressive kernel density smoothing.
Which injects artificial bias into your data. Furthermore, even if you smooth the data, K-bar means requires you to calculate centroids. KL divergence is asymmetric, and it lacks a canonical, mathematically tractable aggregator to find a central cluster point.
So we are basically forced out of information theory and into optimal transport. We need a metric that measures the actual physical geometry of the data.
Which points directly to the Wasserstein metric, specifically the p-Wasserstein distance.
Right.
It metrizes weak convergence. That ensures that if two measures are close in the Wasserstein sense, they are fundamentally close in the classical narrow sense of probability.
The most intuitive way to grasp the Wasserstein metric is through its classic moniker, right? The Earth mover's distance.
Yes, the Earth mover's distance. Imagine your first empirical distribution is a physical pile of dirt.
Okay.
And your second distribution is an empty hole of the exact same total volume, but a different shape.
Got it.
The Wasserstein distance calculates the minimum possible cost, which is defined as mass multiplied by distance, required to shovel the dirt from the first shape into the hole of the second shape.
So it natively respects the geometry of the space.
Exactly.
But the historical problem with the Earth mover systems is that computing optimal transport plans in high-dimensional space triggers a massive curse of dimensionality.
Oh yeah, it usually requires brutally slow linear programming solvers.
So how is it feasible to run this continuously on sliding windows of high-frequency financial data?
The computational barrier vanishes here because the authors are operating strictly in the one-dimensional case. The data lifted from the time series are distributions on the real line.
D equals 1.
Yes. And in one dimension, the mathematics of optimal transport undergo a massive simplification.
The closed-form solution for the 1D Wasserstein distance is remarkable. You do not need a linear programming solver at all.
Not at all. Because all the mass is moving along a single line, The most efficient optimal transport plan is simply a monotonic rearrangement.
You pair the leftmost particle of dirt with the leftmost space in the hole and just move sequentially to the right.
Computationally, that translates to integrating the absolute difference of their quantile functions, which are the inverse CDFs.
Wait, so if you have two empirical distributions with n points, you just sort both arrays of points in ascending order and take the difference.
That's it. Sorting takes O of n log n time. The distance calculation itself becomes a strictly linear, highly tractable operation.
That is incredibly elegant. But calculating the distance is only one component of the k-means algorithm. The other required step is updating the centroids at every single iteration.
Right.
If we are operating in the space of probability measures, what exactly is a centroid?
In that space, the centroid is defined as the Wasserstein Center. It is a specific probability measure that minimizes the sum of the Wasserstein distances to all the other empirical distributions currently assigned to that cluster.
So it is the geometric center of mass for a group of varying market regimes.
Precisely. But finding barycenters in optimal transport is notoriously complex.
I can imagine.
But again, the 1D constraint saves the architecture. For one-dimensional empirical measures that possess an equal number of atoms.
Which ours do, since the window size H1 is constant.
Exactly. Computing the Wasserstein barycenter doesn't require gradient descent. You just take the sorted arrays of all the distributions in your cluster, and for each rank index, you simply calculate the median across the distributions.
Oh, wow. So the resulting array of medians is your new barycenter.
That's it. The efficiency is staggering. You have a non-parametric, topologically robust clustering algorithm capable of finding the geometric center of market regimes, and it runs on simple sorting and median calculations.
Which is amazing. But solving the algorithmic side simply exposes the most difficult conceptual hurdle in financial machine learning.
Unsupervised evaluation.
Exactly. It is the ultimate blind spot.
Yeah.
The market does not provide ground truth labels. We don't get a clean dataset tagging regime A and regime B.
Right.
So even if the Wasserstein k-means algorithm outputs beautifully separated clusters, we cannot just run a standard accuracy score.
No, we can't.
How do we rigorously prove mathematically that these clusters represent fundamentally distinct underlying data-generating processes, rather than just random noise artifacts?
What's fascinating here is how the authors address this evaluation bottleneck. They utilize an integral probability metric called the maximum mean discrepancy, or MMD.
MMD, right.
It serves as an independent, rigorous statistical test to validate the internal consistency of the unsupervised clusters.
For listeners working deeply with kernel methods, the MMD framework is a brilliant application of the kernel trick.
It really is. By mapping the cluster distributions into a universal reproducing kernel Hilbert space, an RKHS,
using a characteristic kernel like a Gaussian radial basis function.
Right. By doing that, we can measure similarities that are completely invisible in lower dimensions. Let's break down the mechanics of that mapping.
Go for it.
The MMD operates as a two-sample test statistic. When you map empirical samples into a universal RKHS, you are computing their mean embedding.
Okay.
The RKHS effectively captures all of the statistical moments of the distribution simultaneously. And because they use a characteristic kernel, the mapping is guaranteed to be injective.
Meaning the mapping is entirely unique.
Exactly. In the RKHS framework, the maximum mean discrepancy between two distributions will be exactly zero if, and only if, the two Borel probability measures are perfectly identical.
So it functions as a true metric on the space of distributions.
Right. Applying this to the clustering output, the authors draw random subsamples from within the newly formed clusters and run a biased MMD test to generate a self-similarity score.
So they are mathematically quantifying the internal homogeneity of the clusters.
Yes. They want to prove that the distributions grouped together actually share deep topological similarities, independently of the Wasserstein distance used to group them.
And the validation results absolutely expose the flaws of the traditional baselines. When evaluated via MMD, the clusters produced by the moment k-means approach exhibit massive internal variance.
They are mathematically chaotic.
The MK-means grouped distributions together that, in the RKHS space, look completely distinct. But the Wasserstein k-means produces clusters that score exceptionally high in MMD self-similarity.
Which is exactly what you want to see. And with the mathematical validity of the clusters proven via the RKHS framework, the actual empirical performance is tested against the SPY index history from 2005 to 2020.
Let's talk about that real-world backtest. They calibrate the algorithm to partition the data into two primary regimes, k equals 2.
Right, aligning with the broad macroeconomic intuition of high volatility stress states and low volatility growth states.
And reviewing the historical backtest, the limitations of Euclidean projection become blindingly obvious. Both MK-means and WK-means successfully flag the catastrophic volatility events.
Yeah, they both catch the 2008 global financial crisis, and they both catch the acute 2020 COVID liquidity crash.
But MK-means fails to detect anything else. It requires a massive singular variance spike to trigger a regime change. It effectively operates as an incredibly computationally expensive outlier detector.
The Wasserstein approach, however, successfully isolates complex structural shifts in the market that don't rely purely on massive variance explosions.
Like what?
Well, it accurately tags the underlying distribution shift at the onset of the Eurozone debt crisis in 2010. It isolates the subtle regime change during the S&P U.S. credit rating downgrade in 2011, and it catches the Chinese stock market turbulence in 2015.
Wow, and MK-means was completely blind to these shifts.
Completely blind because they were nuanced transformations in skewness and tail behavior, not just raw variance scaling.
Now, historical backtesting is useful, but it inherently lacks precision. We can debate the exact day a historical crisis began.
True.
So to definitively benchmark regime on accuracy, the authors shift to synthetic data modeling, where they retain absolute control over the precise timestamps of the underlying structural shifts.
Right. The synthetic benchmarking begins with a geometric Brownian motion model, or GBM.
Which generates continuous, fundamentally Gaussian price paths.
Exactly, because the underlying data-generating process perfectly aligns with normal distribution assumptions. All the algorithms actually perform decently here. The raw moments map cleanly.
Although interestingly, even in this idealized Gaussian environment, the hidden Markov model struggles with the boundary conditions, consistently lagging in identifying the exact transition timestamps.
Yeah, it does. But testing quantitative finance models on geometric Brownian motion is essentially just a warm-up exercise. The critical phase of the paper is the non-Gaussian stress test.
They discard the continuous path and implement a Merton jump diffusion model.
The Merton jump diffusion is literally designed to break assumptions. It takes the standard continuous diffusion process and it injects a discrete Poisson process that generates sudden, massive price jumps.
And these jumps fundamentally alter the geometry of the return distributions, right?
Yeah.
Introducing severe heavy tails and aggressive skewness.
Yes. It accurately models a market that doesn't just drift, but snaps violently.
Here's where it gets really interesting. When those Poisson jumps hit the data stream, the performance disparity between the models is staggering.
Oh, it is brutal.
We look at the regime-on accuracy, which is the metric defining the model's ability to correctly identify the active stress regime. Under the Merton jump diffusion, the hidden Markov model experiences a catastrophic failure. Its accuracy collapses to roughly 0.66%.
Less than 1% accuracy, the HMM effectively dies.
Wow.
Because it relies on parametric Gaussian emission probabilities, the sudden introduction of heavy-tailed Poisson jumps violently violates its core mathematical assumptions. It cannot parse the heavy tails, so it simply fails to transition states.
And the moment k-means projection doesn't survive the jump diffusion either. Its regime on accuracy plummets to roughly 27%.
Because once aggressive skewness and heavy kurtosis alter the shape of the data, the Euclidean distance metric cannot differentiate between the baseline regime and the jump regime.
The L2 norm simply breaks down. But the Wasserstein k-means maintains a highly robust 86.8% regime on accuracy.
It thrives precisely because it operates entirely non-parametrically. It never assumes a Gaussian shape. It never compresses the data into a vector.
So when you visualize the WK-means clusters mapped out in skew kurtosis space,
you see it natively grouping the highly skewed, heavy-tailed distributions of the jump regime based purely on the physical transport cost between the raw empirical realities of the sliding windows.
So synthesizing this core takeaway for your daily machine learning practice, relying on Euclidean space and parametric baselines to govern models on complex, non-stationary data is a massive operational risk.
Absolutely. The shift to operating natively in the space of probability measures using the Wasserstein distance and barycenters bypasses the geometric distortion of vector projections entirely.
Giving you a massive edge.
It provides a mathematically rigorous, computationally trackable indicator for structural data drift, allowing for highly precise model retraining protocols.
Which brings up a fascinating final thought for you to ponder independently. The paper rigorously demonstrates the power of the 1D Wasserstein metric for finding hidden regimes in financial time series. But consider the broader implications of optimal transport.
It goes way beyond finance.
Exactly. If we can lift one-dimensional sequential data into the space of probability measures to uncover hidden nonlinear state changes, how might applying this exact same optimal transport framework revolutionize anomaly detection in entirely different chaotic systems?
It is a profound question.
Imagine applying WK-means to trace subtle phase shifts in neural network layer activations during training, or applying it to continuous biometric data streams, detecting the microscopic structural geometric shifts indicating the early onset of arrhythmias long before a parametric medical model flags a critical variance in heart rate. Once we stop looking at sequences as dots on a line and start analyzing the geometry of the probability itself, the analytical horizon expands exponentially.